So I work in the area of risk, and so I'm always interested in low probability events. And I had never met Dr. Scanlon, and isn't it interesting that she happened to have worked for Stavros? Isn't it even more interesting that she followed Stavros on a program like this? And isn't it even more interesting that it occurred at the National Academy? This is a low probability event. So Dr. Scanlon is a senior research scientist at the Bureau of Economic Geology at Jackson School of Geosciences at the University of Texas at Austin. Her degrees are in geology with a focus on hydrogeology, with a BA from Trinity College in 1980, an MSc from the University of Alabama in '83, a doctorate from the University of Kentucky in 1985. She's worked at the University of Texas since 1987. Her research group assesses sustainability issues with respect to water resources within the context of climate extremes and land use change. They conduct studies ranging from point, that is ground-based measurements, to regional, which are satellite measurements, and temporal scales range from interannual to millennial timescales. Recent studies include evaluation of managed aquifer recharge to even out water storage during droughts and floods in the southwestern United States. She is an associate editor of Water Resources Research and at Environmental Research Letters. Dr. Scanlon? The protocol will be that she will make a brief presentation of approximately 15 minutes, and then we will solicit questions from the audience regarding her particular presentation.
I have it.
Oh, you've got it.
Yeah. Thanks. I appreciate the opportunity to give this short presentation. So I'm going to talk like an auctioneer to zip through some stuff. And I'd like to, I really appreciate that Stavros clarified that recharge was important, because I was about to ditch that from I'm going to talk about sustainable management, or approaches towards sustainable management. And there are a lot of people that I work with from the USGS and NASA and other people that have been doing models. So this is the cast for the recent studies. I'm going to try to address a few questions. Compare global models and GRACE total water storage changes. And then summarize really the models are underestimating GRACE total water storage changes. And I know Jay Femietti will give a lot more detail about GRACE. And then I'm going to talk about the Colorado River Basin a little bit on water storages changes there, showing how we see depletion, multi-year droughts at decadal time intervals, and that the groundwater storage contributes to depletion in the lower basin. And the last thing I'm going to talk about then is how we can better manage. And as Stavros mentioned, when you have rivers and groundwater, you can make it more sustainable. And I'm going to talk about conjunctive use of surface water and groundwater, and then where you actually put the surface water back into the aquifer using managed aquifer recharge, with some examples from the Southwest. So recently we've been comparing global water models with GRACE satellite data, because there's a lot of interest in these global models. So we wanted to evaluate the reliability of the outputs from these. And we did this with about 186 basins that are covering about 60% of the land surface. And here I'm showing the different settings of these basins, arid to humid. So to summarize, when we added up, we're doing the analysis from 2002, when GRACE became available, through 2014. And we added up the net long-term trends in all of the basins. And we come up with the GRACE MassCons data gives us an increase in storage, because we're excluding Greenland and Antarctica. And we get an increase of about 60 cubic kilometers per year. 1 cubic kilometer is about 1.2 million acre feet. And the hydrologic models are showing, global hydrologic models, -6 to -76 over this 186 basins. And then the land surface models, much greater declines, minus 140 to minus almost 500 cubic kilometers per year. So we find that the greatest differences are in large basins, greater than 500,000 square kilometers, in humid regions, and the depletion is focused in the heavily irrigated basins. That all sort of makes sense. So, so if we look at the GRACE data, then here these are the long-term trends in cubic kilometers per year in the different basins from GRACE. And the blue are increases in storage, and the red are decreases in storage. So you can see increases in the Amazon, Parana, Okavango region here, and the yellow means like within the uncertainty envelope. The Ganges, large depletion there, Indus, Brahmaputra, the Euphrates, and increasing in the Murray after the long-term drought. So if we compare, so that's GRACE. This is one of the global hydrologic models, WGHM. And you can see general similarity between the two, but the colors are not as strong because the depletions are less. So for example, the Ganges, here it's minus 12 cubic kilometers per year, here it's minus 7. So small differences in the magnitude of the trends mostly relative to GRACE. And then this is another model, PCR global water balance. These are widely used global models, Yoshiwada and others. And you can see a big difference. So here in GRACE and WGHM, we have an increase in storage. In the Amazon, in PCR, we have a decrease. In the Ganges, in PCR, we have an increase, whereas we have decreases in these other basins. So large differences between these models. And then lastly, land surface model, NOAA, you can see it's dominated by oranges and reds, showing more declines and not really getting the increases that we see from GRACE. So a lot of variability among these models. And really, there hasn't been that much intercomparison. But we're working with all these, the model developers, so that we're sure we're getting the right things. So now I would like to show some time series of the data. And so here in the center, I have the GRACE data, and these time series, then I'm showing the different models. The black is GRACE, the blue is WGHM, and the orange is PCR. These are two global hydrologic models, and then the NOAA is green, is a land surface model. So you can see in the Ganges, then the GRACE is showing, and we just calculate a linear trend. I know that's a simplification. But GRACE is showing a linear decline of minus 12 cubic kilometers per year. WGHM is slightly less, minus 7. And PCR is showing an increase of plus 7 cubic kilometers per year. But you can see pretty good correspondence up through 2009, 2010, and then more divergence. The Indus and the Brahmaputra, similar differences among the models. So then the high basin, the big discrepancy is with the WGHM model, which shows a huge decline, and these are different scales. And so we've been talking to them. They said we saw better correspondence in the past, and that was because they defined the boundary differently and included areas where there wasn't that much change. So they're okay with it. In the Euphrates, then GRACE declined during 2007-2009 drought, but all the models show much lesser decline than GRACE does. And then the Arkansas River, WGHM more decline than GRACE, but the others less. So I know this is about depletion, so I'm just going to flip through these increases. So the Amazon, you can see PCR showing the decline, minus 80 cubic kilometers, and GRACE showing an increase of 40 cubic kilometers. Okavango, GRACE showing a large increase, and the models lesser increases. So the models underestimate the depletion and the increases. Good correspondence in the Murray Basin after coming out of the millennium drought with the models. And then good correspondence between PCR and GRACE in the Missouri, showing the increase there. So this just gives you an idea of the differences among the models, and then differences between the models and GRACE data. And so here I've summarized the results. So with GRACE, showing declines, and then what we see from the models. So sometimes we see lesser declines from the models and then opposite trends in some of the models, like we see here for the Ganges, -12, -7, +7. So there's a lot more work we need to do in comparing these different products. And then this is the increases. So this is the Amazon, gray showing 44 cubic kilometers per year, WGHM 11, and PCR -80. So we have some work. We can't retire yet. Basically, a lot of the models generally underestimate both the depletion and the increases, and then there's a lot of variability among the models. So next, I would like to just talk briefly about the Colorado River Basin. We did an analysis of that a couple of years ago and worked heavily with people at the USGS, Don Poole, and many others. This is the upper Colorado River Basin, and this is the lower basin, and provides water to 40 million people. Irrigation, a lot of the irrigation is outside the basin, and they export a lot of water to California. So the upper basin generates about 80% of the stream flow and huge reservoir capacity with Powell and Meade. So changes in water storage represented the balance between inputs minus outputs, or supply and demand. So if we see a decline in storage, is it because the supplies are decreasing, or the demand is increasing, or a combination? With GRACE, we talk about total water storage, which includes all these different components, but oftentimes we talk about surface water or groundwater, and it's important to recognize that the inputs and outputs could be natural, or it could be caused man-made, anthropogenic. So here I'm showing in the upper Colorado River Basin and the lower basin the demands over time, and the different evaporation, exports, irrigation. Of course, irrigation is very big, but I mean, since 1970s, the demand has been bopping up and down a little bit, more demand in the lower basin because we have Phoenix and Tucson, but really you don't see a long-term trend in the demand. So I think the demand has been fairly stable. So then we looked at, we estimated total water storage to compare with GRACE by summing the reservoirs and the soil moisture data. And so this is the upper basin from 1980, and we projected it back in time from 1980 to 2015. And you can see the seasonal fluctuations, and then we average those out. So basically what we're seeing is declines at about decadal intervals, multi-year declines. So around 1990 drought, around 2000, and then 2011 or so. And then we compared that with the GRACE data. So when we estimated the changes with reservoirs and soil moisture, we get good correspondence with GRACE. So basically we can explain the GRACE data with reservoir storage and soil moisture storage. And so here we show the soil moisture storage, which occurs before the change in the reservoir storage because it impacts runoff. And here are the wet periods, and then the droughts around 1990, around 2000, and this is the blue is precipitation. So I'm not going to go into the details in the lower basin, but again we have these multi-year droughts with declines in storage, and when we just use reservoirs and soil moisture here, we don't fully explain the GRACE data, so groundwater storage is also important. And so here we show groundwater storage increasing during wet periods and declining during droughts. So we looked at water level data, and you can see in the upper basin, groundwater levels are fairly stable over time, so we don't really see a lot of evidence of groundwater storage, so that's consistent with our other results. In the lower basin, then, Don Poole compiled thousands of wells and developed composite hydrographs. And so this black line is a composite hydrograph in the lower basin. You can see increases during wet periods and declines during drought. And then that's mostly explained by water level changes in minimally developed areas in the lower basin. In the active management areas, they had a Sustainable Groundwater Management Act in 1990, so then they implemented conjunctive use and managed aquifer recharge. So they've been pretty stable, except in the irrigated basins that don't have access to groundwater, or to surface water, sorry. Basically, you know, multi-year droughts, it's not changes in demand, it's changes in supply related to wet and dry periods, and then also some pumpage in areas where you have only access to groundwater. So lastly, then, how can we make it more sustainable? We have these wet and dry periods, we need to even out the supply. So conjunctive use and managed aquifer recharge are two of the approaches that we looked at. Managed groundwater storage. So we can, if we want to increase the groundwater storage, we can increase the inputs or decrease the outputs. So we can increase the inputs by natural recharge, just in response to the climate, irrigation return flow, or managed aquifer recharge. And we can decrease the outputs by decreasing pumpage. So conjunctive use then is substituting groundwater with surface water. And they've been doing that in Arizona for quite a while. And then managed aquifer recharge is where you take excess surface water and put it in the groundwater. And groundwater banking refers to sort of both. So this is the Central Valley, and the blue are the rivers, and this is the lower Colorado Basin. And these yellow then lines are the aqueducts that have been developed. The Central Arizona project to take water to Phoenix and Tucson, and the federal and state water projects to take it to the southern Central Valley. And so in Arizona, then after the 1990s, then these active management areas where they had seen a lot of depletion in the past, Phoenix active management area in Tucson, and then they developed this pipeline and brought in Colorado River water, and then they had conjunctive use of surface water, and then they also put Colorado River water into the aquifers through these spreading basins. This is an example of one of the spreading basins, and this is an example of another with an irrigated region in between. This is northwest of Tucson. And this is the southern Central Valley, then Tulare Basin, Claudia Font, and others, a lot of work in this region. So that's Bakersfield. So they bring in all this water. But these aqueducts, you know, they supply water when it's wet, and then they ratchet it back when it's dry because of endangered species issues and others. So they actually can amplify the drought impacts unless you store the water. So this is a schematic from the current water bank of these spreading basins, coarse alluvial sediments, and store it underground. So Claudia's work shows that during drought periods, surface water deliveries decrease a lot, 76, 77, 87 to 92, and then groundwater pumpage increases. So it goes from 70% groundwater during drought to 70% surface water during wet periods. And this conjunctive use then leaves the water in the aquifer, and then in addition with irrigating with surface water, you have that return flow which recharges the groundwater. And now they're talking about, with these extreme events, capturing extreme events in California with flood irrigation. Thomas Harter at UC Davis, flood irrigation, inefficient surface water flood irrigation to recharge the aquifers during the winter periods. So these are the groundwater banks around Bakersfield, and so you can see 76, 77 drought, an increase in banking, and this is the volume of water being stored, and these colors represent different banks. So after the 87 to 92 drought, a big increase in the banking, and the drought in the early 2000s, 2005, 2006, a wet period, put a lot of water underground to store it for the drought, and then recently 2011, 2012. Impossible to get the data now from these groundwater banks. They just don't want to share it. So you can see the cumulative increase in storage from these groundwater banks. And this is Arvin, Edison. They've been practicing this since the 60s. They put the water in during the wet periods, and they yank it out during the droughts. So these multi-year storage systems, I mean, huge investment in this, and this allows them to trade water among users so that the higher value users get it, and it's a nice approach. So in Arizona then, how well does it work? So these active management areas, they practice conjunctive use and manage aquifer recharge. These green areas, they don't have access to surface water or Colorado River water, so they only have groundwater. So if we look at the difference in the composite hydrographs in these active management areas, you can see, fairly stable conditions. But in the areas that don't have access to surface water, it's just depletion, a lot of depletion. It's not sustainable. So to summarize then, I tried to show you some of the global basins and some of the issues with the models, but we need to be using all tools: remote sensing, global models, regional models, monitoring data. Colorado River Basin responding mostly to these wet and dry periods, and then conjunctive use and managed aquifer recharge are good approaches, and I think we'll see more of those in California in the future. And just like to mention the USGS, this Powell Center, where we're looking at combining the GRACE satellite data and ground-based estimates of groundwater storage with people from NASA and the USGS, and we're looking forward to working with this and Lenny and others. Oh, sorry, that's it. Thanks.
Thanks very much. Now we'd like to take a few questions, and if there are more questions than we have time, then we will wait until the end of the presentations of all three people in order to address them. So questions, please.
Yes, you talked about Colorado River, which reminded me of the spill from the Golden Mine impoundments. There have been 40 such failures this year, including the big one in Brazil. So when you talk about water, is it clean water, water available for drinking, agriculture? And if so, how does, the Colorado River, Golden Mine River spill contaminated water over Colorado and 3 states downstream? Is that taken into account into the model, and how do you do that? You have to, if you are considering potable water.
Well, I mean, we're just looking at water quantity issues, and you can see what a poor job we're doing of that. So we haven't even gotten to the water quality aspects. I think we first need to try to get a handle to wrap our head around water quantity aspects. And a lot of other people are working on water quality issues too. I mean, no, we haven't taken into account the water quality
It's more difficult because the impoundment failures you cannot predict.
Right.
Go ahead. Okay. Kim Green, U.S. Department of Agriculture. I just want to mention a recent Center of Excellence that we've stood up at the University of Maryland to really look at sustainable water reuse. And I'm just thinking that we really ought to we have a lot of partners there. It's USDA, it's universities, it's some international organizations that are working with us. But it dawns on me that we haven't really gotten our USGS colleagues involved in sort of helping us with that effort. And so I'll just put that out there. And I know Lenny Koniko's in the room, and I know some other USGS folks are in the room. It just dawns on me that we need to get our groundwater partners working with us at that Center of Excellence.
Right.
Hi, thank you. I'm interested in, you're looking at GRACE satellite data and you're combining it with national groundwater models and regional and monitoring data. Are there any other remote sensing options that may be coming online in the future that you're thinking about including with this analysis?
We try to look at a lot of different evapotranspiration, remote sensed evapotranspiration. I mean, a lot of these models are driven by precipitation, remotely sensed precipitation, and then NDVI, looking at vegetation responding to droughts and things like that. And if I will do any more work on recharge, we're looking at NDVI. So you try to look at as many things as you can. That's why it's nice to have these interdisciplinary groups, with people with expertise in different areas. So ground-based gravity to complement the GRACE data with Don Poole and others, and so yeah.
Yeah, for the uninitiated in water matters, what is GRACE? I'm sorry.
Oh, sorry. It's a religion.
I thought it was one of your Irish cousins.
Well, it was launched on St. Patrick's Day, March 17th. It's a gravity recovery and climate experiment. Thank goodness I don't work for NASA, or I'd be fired, I guess. Right, Jay? Sorry, thanks.
Okay, so one more question and then we'll carry on.
Khalid Aziz from Stanford. I don't know much about water management. I work more with petroleum reservoirs. What are the main causes of the differences between models? Is it the boundary conditions, or is it the way the calculations are performed? What are the key differences in these different models?
Well, you know, that's my next career. So we looked at, say, for example, the high basin where WGHM showed a huge depletion. Their previous publication said that was due to underestimated recharge, but it can't be, because when it's underestimation of extractions. So there's a lot of, and then WGHM is a calibrated model to 14,000 river stage gauges, whereas PCR is not calibrated. So maybe we can compare runs of WGHM with and without calibration, I'm not sure. But you know, so this just starts the dialogue among these different groups. Each group has their own model, so there hasn't been much comparisons in the past.